Okay, so let us talk about interpreting the generalization bound. Essentially, we are trying to describe the difference in theory and practice. Now, if you remember, according to the VC theory, the theoretical aspect says that n is like of the order of 10,000, right? This is the amount of data that we need for a particular epsilon, for a particular probability, the confidence level, right? But practice tells us otherwise, right? So practice tells us that this n is much lower than what theory is telling us. So essentially there exists this difference, there exists this slack between theory and practice. And let us try to understand why there is this slack. Now, if we think about the theory in general, specifically the VC theory, because that's what we've been working with until now, so this theory is general. It's general in the sense that it applies to all hypothesis sets, and then it applies to all learning algorithms, to all input spaces, X, and I would also say to all probability distribution, depending on like from where do we get the data, how the data was generated. So it's applicable to that and to any target function, right? And as a result of this, it introduces some slack that is not required in practice. And because it is general, that's why it's relevant to practice. So it doesn't, I would say, um, the relevance of theory does not go down, so it's equally relevant, but then a slack exists. And let's try to understand the reasons behind that slack. The very first reason for this being an overestimate, theory being an overestimate of the practical aspect of things, is the Hofting bound itself. Okay, so the Hofting bound or the Hofting inequality, this itself introduces the slack. So how? Now, basically, when we derived the Hofting bound, we said that the bound exists for any hypothesis sets, right? So we took into account all hypotheses in a given hypothesis sets, and then we said that this applies to all hypothesis sets in general. Now, when we are looking at a problem in specific, some of the hypotheses within my hypothesis set might not be used at all, right? And I'll never use them for a particular problem. But the thing is that the theory, which is like the Hofting inequality, has to take that into account. It has to accommodate for those cases because then only it will make it valid for any algorithm, any hypothesis set, and all of that. So otherwise, it's going to lose its generality. So in order to accommodate for generality, we make it so general that it becomes like it introduces that slack in there, right? So that's like the first point, why we have that slack. The second one is the growth function itself, the m sub h of n, right? So the growth function, if you remember, it described the number of dichotomies that my hypothesis set can implement through the lens of this n, through the lens of the data, right? That's what we said when we started defining the growth function. Now, the question arises, which n are we talking about? Which data set are we talking about? Well, of course, the worst case data set, right? The worst case scenario. Okay, so then when we are talking about the worst case estimate, then it has to be independent of the probability distribution over x, like where did we get it from, right? And so we have like somehow, if you think about it, built this redundancy to accommodate any data set in this definition, right? And then that, like the thing of any data set is that, of course, it makes the bound general, the theory as general as possible, but then it is including any data set that is introducing some slack in our calculations, right? And then coming to the third point, which is the polynomial bound itself. Okay, so again, if you remember, the bound that we had on the growth function was b sub nk, bnk, not sub, and then this was bounded by the VC dimension plus 1, somewhat close to that, yeah. And so look at this less than equal to sign. This is introducing some technical slack here because again, we are looking at the worst case situation, the worst case scenario, the biggest, right? and which in practice is not the case. And again, there is this additional slack here when we try to define this B and K, if you remember. So we assume the worst case possible again with the given hypothesis set H with a breakpoint K or a breakpoint VC dimension plus 1, right? So both these again introduce some slack, which is why theory and practice are not as aligned as we would like them to be. But that slack is a result of the fact that this theory is general and it's applicable to like almost all problems everywhere, right? So that's why you're kind of paying the price if you think about it in that way. Okay, so having said that, VC bound quantifies approximation versus generalization. We saw some part of it and we're going to discuss even more going forward. So what's going on is essentially you might encounter two cases, right? So one case is that you have a better chance of approximating F. So that means your E in is like really small, but then in that situation, your VC dimension might go up, right? And that would impact your link between E in and E out, which is shown here in this equation. And that link, we have looked at it in terms of the sample complexity, but overall, we can think of this as some model complexity. Okay, so this complexity actually is kind of a link between my E in and E out. And so this is also like the generalization part of my model. Like if my VC dimension was smaller, then I have better chances of generalizing to out of sample error, right? So this link would have been like better in terms of that. So there is a trade-off that's going on. Another view of like looking at this trade-off is that you can have two ways of like solving a machine learning problem. The first one could be that you have a given n, like the customer gives you a fixed n, right? And then some VC dimension is required because you have to create this link between E in and E out, and you cannot like do worse than that. So you need an appropriate hypothesis set, right? So beginning with n fixed, given a requirement of VC dimension, you need some hypothesis set that would work in those conditions and get the best outcome. The second scenario in a practical situation could be that you have a given hypothesis set, right? And so that means you have a VC dimension fixed, right? So this is fixed. And if you have like a hypothesis set known, then you are asked to choose for an appropriate n, right? So n should, like that's the choice that you make because you have to take care of both of these I would say aspects of learning and both working in the opposite direction, right? So in both these cases, this trade-off embeds both these scenarios one way or another. And this trade-off is so fundamental to machine learning that we look at it from another perspective, right? Because VC analysis showed us that the choice of like hypotheses needs to strike a balance between approximating and generalizing, right? Approximating F on the training data and generalizing on test data. Test means something that's new, that's the question that we are trying to answer, right? So what is this like trade-off with another view? And the other view is essentially known as the bias variance trade-off, right? So VC generalization was one way of looking at it. Another way, another analysis is known as the bias variance trade-off or the bias variance analysis. This is like another way of looking at the same approximation versus generalization trade-off. Okay, so what is this bias variance trade-off telling us and how is it different from the VC theory? Now, in VC theory, these are the two questions that we were trying to answer, right? How well did the learning approximate F in my in sample, right? And then the second question was, how close is my in sample error to my out of sample error, right? So that like, how well was your algorithm in reaching from E in to E out? Okay. Now, as opposed to these two, which is like my VC theory, this is my VC theory, my bias variance analysis is answering sort of similar questions, and we're going to establish like some kind of a relationship between both. But it's like answering a similar question in a slightly different manner. So how well can the learning approximate F? Okay, what does that mean? Let's draw a picture, and let's say this is my F, which is obviously unknown, right? And then here's my data. Here's my training data, right? So I have like these different points, right? And let's say I come up with this as my final G, right? This is my final hypothesis that my learning algorithm or whatever came up with, right? So essentially, this first question is asking us what is the difference between the G that you came up with and F? Because like my goal was to get an F, and I tried to come as close as possible to F, but then this was my limitation, right? There were like a number of limitations, and I could come only as close. So this difference between where my G is and my F is essentially my bias. How like how well can the learning approximate F? So that's like the first one. That's my first question I'm trying to answer. The second one is how close can you get to that approximation, this approximation, with a finite data set, right? So basically what I'm trying to answer is how well or how easily can you find the best hypotheses? How well can you find this G, right? And this is data dependent. Why is this data dependent? That's because let's say this was my training set, but now I have a bigger training set, right, with lots of other possibilities. Now you see that this F somehow comes inside that larger data set. The larger the data set, the higher the chances that I'll come close to F. And of course, I will come to close to F, but the cost of searching itself, because you can see there could be a lot of variability because my data set or my search sort of domain has exploded, right? Although I can come close to F, but there is this with a finite data set, right? So basically to find that best G, I have to get into the data, and then depending on which data set you have, you will have this variance around your best function, right? And that variance is known as the variance component in this bias variance analysis. So the first question is essentially pointing towards bias. The second question is pointing towards variance. Okay. So bias variance analysis, you might be wondering why we haven't looked at it yet, is because it mostly applies to squared errors, so regression problems mostly. Mathematically, that's how it was derived, so regression problems. But of course, we can heuristically, this is a heuristic essentially now, and we can apply it to classification as well, right? The fundamental idea remains the same, whether regression or classification. Okay. Another additional point that I wanted to make was that this bias variance, like in VC analysis, we were mostly focused on our hypothesis set, right? But bias variance analysis will take into account the learning algorithm itself. So basically, it's saying different algorithms can have different E out when applied to the same hypothesis set. To quickly give you an example of what I mean by this is that let's say I have like a final some hypothesis H1 here, right? So taking care of the algorithm means that let's say your algorithm is so naive, whatever the algorithm is, and it picked up this H1. And then it always picks up H1 no matter what data changes I do, no matter what data set um, generate initially, it just picks up this H1. So basically this indicates that there is no variance, but there's a huge bias, right? So there is basically, it's indicating there is something off about this entire process, about our algorithm, right? So we can like maybe take some action or do something about it, right? But our VC analysis wouldn't know that. But bias variance trade-off would tell us that. So that's what this particular part means here. Okay. So having said that, let's move on to further like trying to understand this example with a relationship between bias variance and the VC analysis. So let's look at this simple learning problem. So let us assume we have like this graph f of x, and I know my target function, which is like the sine curve. So I'm looking at something like this, right? So let's say this is my target function, okay? And I have, and again, like let me have two hypotheses set. So that's why I've just like wanted to kind of compare them. So let me, not sure if I'll be able to draw the exact same thing, but yeah, it looks similar. F of x, and this is here is going to be my x. So anyways, okay. So let us say my initial data is like these 2 points. Let's assume these are the points, and here and here looks kind of okay to me. Okay, so I have, let's say, beginning with two hypothesis sets. So the first one is I'm labeling it as H0. My H0 is essentially the equation of a flat line. So all equations of flat line that are parallel to this x-axis essentially. So flat line, basically zero slope, right? So maybe you can think of this equation as like this hypothesis is h of x equals b, and then this b can change, it's a constant, right? So if we have such a hypothesis set, let's say we keep, basically what will happen is you can like plot lines on this graph, right? Parallel lines to the x-axis, and eventually you'll get some average because I just have like two data points. So my final hypothesis is going to be somewhere here, like the average of these two, right? The average distance between them. And I'm looking from the perspective of a regression problem. Let's say this is this is my g of x. And let me label it as G0 of x because we have two hypotheses. So the second hypothesis that I'm looking at, or the hypothesis set rather, let's call it H1. And the set is a line with a slope. Line with a slope. Well, some like this form, ax plus b, right? So basically now this is like slightly more complex than this one, right? Because I can change two parameters here and I can change like the intercept and the slope, right? So because this is like more complex, it gives me the ability to sort of really fit in a line like this, right? So this is my G1 of x. Okay, everything is awesome. Because this is a machine learning problem, so obviously I will predict for something that's unknown, right? So let's say that prediction point or my x, that unknown is here. So it's again going to be here as well, right? And obviously my prediction would be something that falls on this, right? So this is my predicted value according to this hypothesis set. So this is predicted, right? And similar to that, my x, let's say, is here, right? And if I draw a line, well, this is almost like zero error or like very small error, because error is essentially going to be this part, right? So this is a line, obviously this is going to be line, but this is going to be my error or my prediction error, right? How close I am to the target function. So my target function was my sine curve, and this is my predicted value according to this hypothesis set. Similar to that, my predicted value here, as you can see, and this is like almost there, right? It's actually on the very close to the target function. So whenever we are examining like a test point, the way to quantify the difference between my predicted value and my like the actual value is using the error term. So basically the error here, which I'm calling error 1, is going to be f of x, because that's my function, minus the predicted value for that point x squared. As we said, the bias analysis is usually done for regression, and so the error term is the squared term, and so that's why we're using that. In this situation, it's going to be f of x, because the target function is still the same, g1 of x whole squared, right? Because my predicted was like slightly different in this case. And just like by looking at the graph, I can tell that this one is way better than this one. Okay, so having done that, let's say like this was like 2 points data set, right? Let's say I have like the same hypothesis set, everything is the same. And let me again draw this, right? And okay, no, I don't want the line. I shouldn't have done that. Okay, good. So going back to the curve. Yeah, first I should have the data, right? I cannot predict without the data. So let's say my data has changed a little bit. So this is my new data point essentially, and this is my f of x. This is the same line, h of x equals b. And then here again, as I said, my data has changed a little bit, right? And so this goes like this. And here again, the same data points and f of x. And the hypothesis set is ax plus b. Now, what should we do now if I have this kind of a like a data distribution? Again, my line here wouldn't change a lot. So if you remember, the predicted point was somewhere here. My error, if you look at this part, hasn't changed much, right? But because I have the flexibility, more flexibility here to change x and to change a and b, so I will definitely come up with this exact line, right? And if you remember, my x was here, right? So the error becomes huge just because I have a different data set, right? So depending on like this new huge error, what should we be able to do? Should we have like some kind of analysis, right, from generating the data to fitting a hypothesis to getting an expectation of error? Because we can have different data points, and depending on that, like in the previous example, this hypothesis was really good, right? But in this example, it's bad. Similarly, this didn't change much, right? There was like no um, I would say observable change. Right? So which of these two hypotheses is a better one, and should we have a more sort of a quantifiable way of comparing hypothesis sets? So we're going to answer those questions in the next video. So that's it.